Let's talk a little bit about Gaussian and Gauss Jordan elimination. These processes are used to solve systems of linear equations, much like doing elimination that we just talked about today in class, was going through and trying to eliminate variables and figuring out specific values for variables. So when we do this, we're actually talking about doing the operations on that augmented matrix that we talked about today in class, the augmented matrix associated with the system of linear equations. And our goal is to put it into a form where we can read off the solution easily. That form is referred to as row echelon form or reduced row echelon form. So let's do the definition of reduced row echelon form here. So we say that a matrix is in reduced row echelon form if whenever you have a non-zero entry of a row, the first one, the first to the left is what we mean, is always a 1 unless that row is a row of all zeros. Then I can't have a 1 as the first non-zero entry, obviously. That first one, we call it a leading one or a pivot. All rows of zeros that we potentially have are all put down at the bottom of the matrix. And if we have row I is farther to the left than, if row I is less than row J, what I mean is row I is above row J, so the I is less than J, and they both have leading ones, then the leading one in row I is farther to the left. It's in a leftmore column than the leading one in row J. And then finally, each column that has a leading 1 has zeros above and below the leading 1. If we have a matrix that satisfies 1 through 3, then we have what's referred to as a matrix in row echelon form, but not reduced row echelon form. It's that zeros above and below the leading 1 that makes it reduced row echelon form. Notice that 1 through 3 actually imply that they must have zeros below each leading 1, because remember the leading 1, as you move down rows, your leading ones have to go farther to the right. So there have to be zeros below each leading 1 to be in row echelon form. To be in reduced row echelon form, not only do there have to be zeros below the leading 1, but there also have to be zeros above it. So, looking at this particular matrix, we see that this is in row echelon form because our leading ones here in the first row is that one, second row is that one, third row is that one. So the leading ones here, as we move down, the leading ones move to the right. Notice we have this nice triangle of zeros, if you will. But it's not in reduced row echelon form because if I go above this 1, there aren't zeros. These would have to be zeros to be in reduced row echelon form. So this is row echelon form, but not reduced row echelon form. Notice this column isn't affected by whether or not it's reduced row echelon form because there's no leading 1, no pivot in this column. All right, so again, the reason why we want to be in reduced row echelon form or row echelon form is so that we can determine solutions to systems of equations. So here's our augmented matrix. Suppose you have this as an augmented matrix. Well, if we convert that back to a system of equations, well, we see that we have 1x1, 0x2, 0x3 equals 5, or x1 equals 5. This one says that x2 equals -2. This one says that x3 equals 1. So notice this is in reduced row echelon form, and I can just read the solution right off. That's one of the reasons why we like the reduced row echelon form. So to put them in reduced row echelon form or row echelon form, we do elementary row operations. We talked a little bit about that in class today. There are 3 of them. The first one is multiply a non-zero row, or a row by a non-zero constant. So that has the effect of multiplying or dividing both sides of an equation by a number. Of course, we don't want to use 0 for that because we can turn a false statement into a true one by multiplying both sides by 0. So that's why we say non-zero constant. Exchange 2 rows, we didn't see that one in class today, but all we mean by exchange 2 rows is literally just swap the rows. Well, that just has the same effect as changing the order of the equations. That's not going to change the solution set. The last one is add a multiple of one row to another. We saw that again today in class where we were taking a multiple of the first row and adding it to the second row and so on down the line. So when we solve a system of equations by using elementary row operations, we're doing what's called Gaussian elimination or Gauss Jordan elimination. The only difference between the two is Gaussian elimination, we put it in row echelon form. Gauss Jordan elimination is we go ahead and put it in reduced row echelon form. So let's look at the steps, the first thing we want to do is you always want to get a leading one in the first row. So we do that. We can do that by the first elementary row operation by multiplying or dividing by a constant. But sometimes you have an easy row swap or an easy addition that you can do that put that leading one in the first row. The next step is to get zeros below that leading one. Move any rows of zeros that you get to the bottom, in case you get any. There might be some cancellation that you do, so you need to move those rows of zeros to the bottom. And then you repeat for the second row, the third row, and so on down the line until you're finished. That's Gaussian elimination. If you want Gauss Jordan elimination, instead of just worrying about getting zeros below the leading one, you'll get zeros above and below the leading one. That's Gauss Jordan elimination. All right, so just as an important side note here, and I'll mention this again when we go through a couple of examples, if you're trying to get a leading one in row 3, don't try to use a multiple of row 1 or row 2 to get the leading one in row 3, because you've already got non-zero entries over to the left of that leading one that's supposed to be in row 3. If you try to add 1 or 2 to it, you're going to be sticking non-zero things back over there and undoing what you just did in the previous steps. So when you're trying to get a leading one in a row, either always work with a row below it, either swap out a row with it, or do a multiple, add a multiple of the row below it, or multiply the row by a non-zero constant. Never, ever, ever work with a row above to try to get a leading one in a row below. It just won't work. All right, let's do a couple of quick examples here to see to put these methods into motion here. Here's a system of linear equations. Our first thing that we do with this system of linear equations is put it in our augmented matrix form. So again, remember, that's just a matter of writing down the coefficients and the constants. We put that vertical bar in there just basically to separate the coefficients for the variables from the constants. All right, we already have a 1 in the upper left-hand corner, up here in row 1. So a Gaussian elimination says I now need to get zeros below it. To get a 0 below this 1, I need to multiply row 1 by 1 and add it to row 2. So literally just take row 1, add it to row 2, replace row 2. To make this a 0, I need to do -3 times the 1 and add it to the 3. So -3 times row 1 added to row 2. Added to row 3 and replace row 3. If you do that work, here's what you get. You can check those answers, but you'll get the zeros here, and you get this this row, -159 for row 2, -10, -2, -14, row 3. Again, remember these elementary row operations don't actually change row 1. We're just doing that multiplication there as an intermediate step to help get rid of those constants, in this case the -1 and the 3. Now, we need a leading 1 in row 2. Well, the easy way to do that here is just to make this negative a positive, so we'll multiply row 2 by -1 and replace row 2. All that does is flip all the signs in row 2. And then remember, for Gaussian elimination now, we got this leading 1. I want a 0 below it. To do that, we need to take 10 times row 2, add it to row 3, and replace row 3. And we get this new matrix. Notice again, now we've got this nice triangle of zeros below this diagonal, if you will. Last step is we want to change this to a 1. To change this to a 1, I need to divide by -52 or multiply by -1 over 52 to get this augmented matrix. All right, so the last matrix that we saw was in row echelon form. The Gaussian elimination process is done. We're finished. And then that augmented matrix corresponds to this system. Notice immediately we get x3. Since we have x3, we can get x2. Once we have x2, we can use that to get x1. This is referred to as back substitution. So using that back substitution, if you plug in 2 in for x3 and solve, you'll get that x2 equals 1. Plug in 1 for x2 and 2 for x3, and you'll get 3 for x1. So you can see again why using the Gaussian elimination is a straightforward way to get the solution to the system of equations. Let's do one with Gauss Jordan elimination. All right, so here's our augmented matrix for the system. Notice the first step is to get a 1 in the upper left-hand corner. Right now I have a 0. So we'll swap 2 rows. Doesn't matter which ones. I just need to get something that's not 0 up here. So I swapped row 1 and row 2. Now I need to make this a 1. So if I make that a 1, I need to divide everything by 3 or multiply by 1/3. So we'll have 1/3 of row 1 and replace row 1. I need to get zeros below this 1. I've already got a 0 in row 2. I just need a 0 in row 3. We'll accomplish that by doing -6 times row 1 added to row 3 and replace row 3. You can check that arithmetic gives you the -699 in the third row. Now we need a leading one in row 2. So I need to get this -2 to be a 1. So we'll just multiply by -1/2 in row 2 and replace row 2. Now here's where Gaussian and Gauss Jordan elimination differ, but they're really the same process. It's just a matter of doing a little bit more work. For Gauss Jordan, I need to get zeros above and below this 1. So to get this 2 to be a 0, I'll multiply by -2 times row 2 and add it to row 1, replace row 1. To get this -6 to be a 0, we'll do 6 times row 2 added to row 3 and replace row 3. You can check that this is our answer. And now I could continue, but I actually am done solving this system of linear equations. The reason why is look at this last equation. This last equation says that 0 equals 6. That's impossible. So this system has no solution, and the word we use for no solution is inconsistent. We'll do more examples of these in class, but I wanted to give you an idea of the process, and I'll show you a little bit with the calculator in class, and then we'll also post a video with calculator instructions on how to do row reduction on your calculator.